Hydrology, Measuring Probability, Chapter 3, Lecture 2. I'm Dr. Marty Matlock. Let's get started. From a previous lecture, we discussed frequency analysis. Now that we know why we need to know the frequency of events, rainfall, runoff, peak flows, etc., how do we calculate them? There are 5 cases we encounter when calculating these frequency of events. Case 1, we have a reasonably long period of record of events for the location of interest. Case 2, we have a reasonably long period of record of events, but not for the location of interest. Case 3, we have a short-term period of record of events for the location of interest. Case 4, we have a short-term period of record of events, but not at the location of interest. And case 5, we have no records in the vicinity of the location of interest. And the location of interest, of course, is usually the catchment or watershed in which we're designing a hydrologic feature. Unfortunately, most of the time in the U.S., engineers are dealing with case 5 because we design in small watersheds or catchments with little monitoring or rainfall data proximate to the design site. Rarely do you have a weather station that's been in place for 100 years right next to what you're designing. Sometimes you do, mostly you don't. However, we have to understand how to deal with the preceding 4 cases in order to address this last case. So we'll review basic probability theory through this lecture. We have a guiding document, The Statistical Methods in Water Resources by Helsel and Hirsch. It's available in our readings. It's also available online, free. The USGS documents are incredible for this. This is book 4, Hydrologic Analysis Interpretation. This is how we take information and make it data. Then we put the data into more general context to make it knowledge, and then we assess that knowledge over time to analyze probability and risk. This is our process. From the document, when determining how to appropriately analyze any collection of data, the first consideration must be the characteristics of the data themselves. Little is gained by employing analysis procedures which assume that the data possess characteristics which in fact they do not. The result of such false assumptions may be that the interpretations provided by the analysis are incorrect or unnecessarily inconclusive, that is to say, wrong. We know from your basic mathematics classes and calculus and others that time series of information can be represented, or any series of information of data can be represented as probability distributions. And we know that there are discrete distributions, which are categorical blocks of information, like the Poisson binomial, geometric, negative binomial, hypergeometric distributions. You see those as bar charts. And then there are continuous distributions, which are represented as lines and which are mathematically represented by continuous functions. Some function of x equals, in the normal distribution you can see to the right, we can define the probability of, or we can define that distribution if we know a couple of things. If we know x, we know the mean, we know the standard deviation, and the standard deviation, and mu equals the mean, standard deviation equals, and sigma equals s sub x, standard deviation. We can calculate a normal distribution. We can do the same with the log transform versions of the mean and the standard deviation to create a log normal distribution. Exponential values, we can characterize the distributions if we know x. So these are fairly well-known and understood distributions. It's important that you see each of the distributions, though, for their strengths and weaknesses. The most common distributions we use in hydrology are the log normal distribution, because it's bounded on the left by 0. It's bounded on the right by positive infinity, which means it can allow for extreme data. This is the most common way to express typical data observed in hydrology. Now, sometimes a normal distribution is used as well, where there's a central tendency, a centroid that's at the mean. The normal distribution is bounded on the left and right by positive and negative, or negative and positive infinity respectively, which means that in order to use this in hydrology, you have to truncate that. So the negative isn't, or the left side is usually like 0.1, and the right side maybe 3,000. And so you truncate, and then you have a mean that's somewhere in the middle, say 1,500. And that's the typical way to express a normal distribution. And there are other variants of that. The Rayleigh distribution is a variant of the log normal distribution. Maxwell-Boltzmann is the same way. And you can see throughout, we have the F distribution. There are others. These distributions, it's not necessary that you memorize for this class the probability distribution functions, PDFs, not to be confused with the document format, but the probability distribution functions, which you see in these graphs on the left. It's important that you recognize what those are. So if I showed you a graph of a log normal distribution, you ought to be able to say that looks like a log normal distribution. Now, it could be Maxwell-Boltzmann or Rayleigh or something, or an F distribution, but it looks like a log normal distribution. And the same way with a normal distribution. You should be able to distinguish those two types visually. Now, probability distributions take discrete data, see the bar charts on the left, and you plot a histogram of discrete data, and then you can infer from that a distribution, a continuous, from discrete data with bar charts to a continuous data set, the probability distribution function that represents the data. Now, if you plot these as a cumulative graph where each bar is added to the next bar, then what you end up with is a cumulative distribution function. The relationship between the PDF and the CDF should be pretty clear to you. The CDF is just the cumulative risk. The CDF is bounded on the y-axis from 0 to 1, 1 being 100%, 0 being 0% probability of an event. The PDF is bounded by whatever the upper proportion is. It could be 30% or 50%. So typically in a normal distribution, the peak is at 50%, and that peak is right about the middle of the inflection point for the CDF, 50% here, but it goes all the way to 100 and asymptotes out. The CDF is the more useful of the two diagrams because cumulative probability is really more useful for predicting risk than a PDF. But you develop the CDF from the PDF. You have to understand them. The relative frequency and cumulative frequency functions provide probability estimates for classified sample data within categories or classes from 0 to 1, 1 to 2, 2 to 3, etc. The relative frequency function, f of x, is a discrete sample approximation of continuous probability function for the entire population called a probability density function, the PDF. There are some important differences between the PDF and relative frequency function. Whereas the relative frequency function, which you can plot in Excel, gives probability estimates for intervals of the variable x, the PDF shows it as a concentration or density for intervals of x along the abscissa, the x-axis. The relative frequency function gives probability and ranges between 0 and 1, but the probability density function ranges from 0 to infinity. The third difference is the relative frequency function is dimensionless, whereas the probability density function has dimensions of x to the minus 1. The sample cumulative frequency function, fsx, has a continuous counterpart for the population called the cumulative distribution function, f of x, for the cumulative distribution function. Both functions give probabilities. Both range from 0 to 1. Both are dimensionless. Here's what we're talking about. So if we look at a typical normal distribution where f of x is some range from x to minus infinity as a function of some mean over some mean with respect to the mean, and f of x is the derivative of f of x, then we can see that the change of f of x over x is the f of x. Now, what does this all mean? It means we can calculate area under the curve based upon standard deviations from the mean. So in a typical normal distribution with a central tendency, half of the data are on the right-hand side of the mean, half the data are on the left-hand side of the mean. One standard deviation to the right and one standard deviation to the left represents 68.26% of all the data under the curve. 1.96 standard deviations left and right, 1.96 standard deviations to the left and right gives you 95% of the data under the curve. Water resource data share the following characteristics. Lower bound of 0, no negative values. The presence of outliers, things happen that are extreme. Observations considerably higher or lower than most of the data, which infrequently but regularly occur. Outliers on the high side are more common in water resources. Positive skewness due to items 1 and 2. Values of an observation on the horizontal axis are plotted against the frequency with which that value occurs. The density functions are like histograms of large data sets whose bars become infinitely narrow, giving you a continuous line. Skewness can be expected when outlying values occur in only one direction, and they almost always occur in the extreme high-end right side direction. Non-normal distribution of data due to those three issues. In addition, symmetry does not guarantee normality. Symmetrical data with more observations at both extremes than occurs for a normal distribution are also non-normal, that is, heavy tails. That can be a bimodal distribution. Be wary of that because averages mean little when all your data occur on the extreme left and extreme right. Data reported only as below or above some threshold. Those are censored data. Examples include concentrations below one or more detection limits. That's why 0 is such a dangerous number in statistics. Annual flood stages known only to be lower than a level which have caused a public record of flood. The hydraulic heads known only to be above the land surface, like an artesian well on an old map. Seasonal patterns. Values tend to be higher or lower in certain seasons of the year. Autocorrelation. This is really dangerous too, to make sure that you're aware of. The consecutive observations tend to be strongly correlated with each other. For the most common kind of autocorrelation in water resources, positive autocorrelation, high values tend to follow high values, and low values tend to follow low values. During a flood, you have a high flow event day 1, a high flow event day 2, a high flow event day 3, etc. During a drought, you have low flow events during those periods. These are not independent events. Dependence on other uncontrolled variables. Values strongly covary with water discharge, hydraulic conductivity, sediment grain size. Land use is a big one. So we have a period of record of flow in a watershed, runoff, and therefore flow in a stream. And we rely on that period of record, and that period of record may be 100 years long. And for 80 of that 100 years, where we have that period of record, it was a forested watershed. But in the last 20 years, it started developing. In the last 5 years, the watershed has become intensely urbanized. That period of record is of little use then in predicting what will come next because the runoff has changed dramatically because of land use change. These are things we have to be aware of. You're all familiar with basic statistics, but we're going to review them anyway. The classic measure, the mean. The mean X is computed as the sum of all data, X sub I, divided by the sample size N. So that's the mean. For multiple groups, the weighted mean of a group, I, the overall mean, can be weighted by the number of observations in each group. So if you have clusters of groups, say you have 30 observations in one stream, 50 observations in another stream, 20 observations in another, you can take the mean of those and you can weight them based upon the number of the ratio of observations. In Excel, this is just simply average over the range, and you could do that manually for the weighted means. We've already seen normal distributions, log normal distributions. Familiarize yourself with the relationships between the mean and the medians. In a log normal distribution, the median, which is the centroid of the mass under the curve, is usually to the left of the mean because the mean is influenced by the extreme values to the right. The mean and median are usually equal in a normal distribution with a central tendency of data. Here's another way to think about the impact of means and outlying data and medians. If you think of the mean as a triangle of data on a that is the center balance point for data on a big beam, and the most extreme data point out here Think about the lever arm. So you have a big lever arm about the moment, which creates a significant amount of force, which disproportionately influences where the balance point is, where that triangle has to be placed. If you take that point away, look at the length there. That's called an outlier or an extreme event. If you take that, that produces a significant amount of downward force. If you take that away, you reduce that pressure and it adjusts, and the mean adjusts. Notice that the mean between these two positions has moved to the left significantly by taking this outlier out. Now, outliers are a dangerous term because outlier implies somehow that it's not credible, when in fact in hydrologic events, the extreme events are the defining events. They're the floods, they're the droughts, they're the things we manage for and try to manage risk against. The midpoint, or 50th percentile data point, is the median. This is the data point with equal numbers of observations above and below it. So if you take all the observations and so you have 100 observations, the 50th, the difference, the median is between the 40 is the 50th observation. If you have 101 observations, it's between 50 and 51. So it's the average between the two. So when it's odd, you divide the sort of the 50th and the 51st. When it's even, you just take the midpoint. And you can find this in Excel with just median for a range of data. The median is minimally affected by extreme observations. So it's a valuable measure of sort of that central tendency of the data. The mean, here's an example, two examples where we have means and medians. The mean increases from 8.1 to 23.6 when the largest number goes from 12 to 120. So that simple change. The median, which would be 7 plus 1 divided by 2, or the fourth lowest data point, is unaffected by the change. Notice how this was done. We had 1, 2, 3, 4, 5, 6, 7 data points. So the midpoint is the data point of the fourth data point, 1, 2, 3, 4. So it's between those. The geometric mean is the mean of logarithms transformed back to original units. So geometric mean is expressed as the exponent of the log transformed averages. So you take all the observations, transform them to logs, and take the average of those, and then take the exponent of that. It's a natural log base e. It's a log, an inverse of natural log e to the x is exponential of x. You can also calculate this by, instead of doing the sum of all the x observations, you could do the product of all the x populations divided by the in root. If you have 30 observations, you would do the 30th root of all the product of all the observations. So you would say observation 1 times observation 2 times observation 3, multiply all those together and divide those by the in root, 30th root of all of those. And that also gets you the geometric mean. It tends to be close to the median. You can do this in geomean range. And this is often used with water quality data in particular, where you have extreme events, but you're trying to understand the system from with less dramatic impact from those extreme events. Measures of spread are critically important. The mean gives you the central tendency and the median, but measures of spread are critically important. Sample variance is the most common measure of spread. S squared equals the sum of all the differences of each observation from the mean squared over n minus 1. This is var.s range in Excel. The standard deviation is the square root of that. So you just simply take the square root of s squared and you get s, standard deviation. So why do we use s squared? What's the sample variance? Well, the sample variance is an absolute value, and taking the square root of that's possible now. So the standard deviation of the range, dot s of the range, gives you s. S is one of the most commonly used statistics. The mean and s, with those two, you can almost calculate everything. Coefficients of variance is a very simple concept. It's the proportion of the variance of the standard deviation over the mean. It's times 100. So a coefficient of variance of 10% means the standard deviation is 10% of the mean. Or a coefficient of variance of 0.1, you'll sometimes see it expressed as 0 to 1. It won't be multiplied by 100. You have to be able to understand what that is and not know it as 0.1%. So that means you better understand this is one of the inconsistencies used in CV. It's generally always expressed as a percent or as times 100. And it can generally, it can be greater than 1 because you can have a standard deviation that's greater than the mean. It's a very powerful way to express the spread because it is standardized to the mean rather than an absolute value. It can be expressed as the spread of data in proportion to the mean. And so you just calculate it directly in Excel. I'm sure there's a function in Excel to do this. I just don't trust it, so I calculate it manually. Another measure of spread is the interquartile range, IQR. We have acronyms for everything. IQR is defined as the 75th percentile minus 25th percentile, which gives you the 50th percentile. So it's the quartile distributions, 75th, 50th, and 25th percent. You only have to calculate 3. 50th is a median. And you split these into 4 equal sized quarters, and then you can plot those with the extreme data, the minimum and maximum data through a line, and you have whisker plots. The 75th percentile, also called the upper quartile, is a value which exceeds no more than 75% of the data, and is exceeded by no more than 25% of the data. The 25th percentile, inversely, is the lower quartile, and a value which exceeds no more than 25% of the data and is exceeded by no more than 75% of the data. So you can see how useful this is in visualizing the data. I like probability distribution functions, because like a normal or log normal distribution, because I can see them more clearly, but these are other ways. Skewness is a measure of the asymmetry of data around a mean or median. So in a normal distribution, there's a central tendency, and the mean and median are centrally located. In a log normal distribution, you can be skewed positive to the left of the mean or negative to the right of mean. And that skewness is a function, is a characteristic that is measurable and quantifiably calculatable. When data are skewed, the mean is not expected to equal the median, but is pulled towards the tail of the distribution, one way or the other. So in this case, the data is skewed to the left. The median data are skewed below the mean. Thus, per positive skewness, the mean exceeds more than 50% of the data. That's the case here. This is positively skewed. The mean is greater than 50% of the data. The median is 50% of the data. The mean is positively skewed. So this is not where the curve leans. This is where the mean is relative to the median. Positively skewed means that the mean is larger than the median. Negatively skewed means the mean is less than the median. Standard deviation is also inflated by the data in the tail. Therefore, tables of summary statistics which include only the mean and standard deviation or variances are of questionable value for us because we don't understand their skewness. Mean and standard deviation reported may not describe the majority of the data well. Both will be inflated by outlying observations. Summary tables which include median and other percentiles have far greater applicability to skewed data. So that's why it's important to also show the median of your data when we're reporting flows, when we're reporting rainfalls. Means and medians are equally important because you can see the skewness of the data. You can see whether it's positively or negatively skewed. Skewed data also call into question the applicability of hypothesis tests, which are based on assumptions that data have a normal distribution. So the more skewed the data, the more difference the median is from the mean, the more difficult it is to use parametric statistics like t-test, because if the data are skewed that much, then the t-tests do not adequately predict the probabilities of containment of the data within a distribution, like we saw a few minutes ago. Here's examples of positively skewed and negatively skewed. So here, in this case, the mean is larger than the median, the mode, which is the peak, the median, which is the centroid. The mean is larger, which is positively skewed. Here's symmetrically distributed, In this case, the median is larger than the mean. The mean is smaller than the median, so it's negatively skewed. These are important characteristics. A log normal distribution is almost always positively skewed. Measures of skewness given as G or gamma, really it's almost always gamma, but sometimes people have trouble with Greek letters, is the skewness measures used, the coefficient of skewness is most often used. It's adjusted third moment divided by the cube of the standard deviation. N number of observations divided by n minus 1 times n minus 2 times the sum of the difference between each observations and the mean cube over the standard deviation cubed. A right skew has a positive G, a negative skew has a negative G. You can calculate this in Excel with just skew and the range of data. Excel's very nice. Outliers can have one of three causes: measurement or recording error. You'll see that in your rainfall data where you have 999 or negative 999s. Those are measurement errors. That's the actual indication from the system that it's got a measurement error. An observation from a population not similar to that of most of the data, such as a flood caused by a dam break rather than by precipitation, something weird happens. A rare event from a single population that is quite skewed. Outliers are often discarded in order to make the data fit nicely into preconceived theoretical distributions such as the normal distribution. This is called bias. Sometimes the bias is a necessary adjustment, and as long as it's articulated, as long as it's clearly defined and clearly disclosed. But it's also dangerous when it's not clearly defined and clearly disclosed, because bias then becomes a form of data bigotry where we have a misperceived notion of the phenomena we're analyzing. The entire data set may arise from a skewed distribution, and taking logarithms or some other transformation can produce quite symmetrical data. So there's a way to take non-symmetrical data, like log normal distributions, and make them symmetrical in a way that allows us to then perform parametric statistics on them. But even if no transformation achieves symmetry, outliers don't have to be discarded. Rather than eliminating actual and possible important data in order to use analysis procedures requiring symmetry and normality, procedures which are resistant to outliers should also be employed. Most parametric or probabilistic statistical analyses depend on data being normally distributed. The z-tables we use for calculating probability distributions are based upon normal distributions. Skewed data violate this requirement. Data often need to be transformed in order to meet the criteria. Transformations are used for three purposes: to make the data more symmetric, to make the data more linear, and to make the data more constant in variance. High degrees of inconsistency and variance can also make data non-comparable. Now, transformations are not bias because you're doing this on purpose to all the data. They are mathematical adjustments to observations so they can be statistically analyzed. One unit of measurement is no more valid a priori, that is in the beginning, than any other. For example, the negative logarithm of hydrogen ion concentration pH in solution pH is a valid measurement of a system as hydrogen ion concentration itself. Just because we take the negative log doesn't make it less valid. It just makes it a different kind of use. We can actually plot pH linearly as opposed to exponentially. Transformations like the square root of depth to water at a well or cube root of precipitation volume should bear no more stigma than does pH. There's a reason we're talking about this is because there's a lot of resistance from a lot of folks who don't know any better about data transformation. The objectives for use of transformations are those of symmetry, linearity, and homoscedasticity. That's your big word of the day. Homoscedasticity, which means equal variance. That is, the skedasticity is homogeneous. The variance is homogeneous. So homoscedasticity is a desirable characteristic in our data. In order to make an asymmetrical distribution become more symmetric, the data can be transformed or re-expressed into new units. These new units alter the distances between observation on a line plot. The effect is to either, remember our balance beam, The effect is to either expand or contract the distance to extreme observations on one side of the median, making it look more like the other side. The most commonly used transformation in water resources is the logarithm. Logs of water discharge, hydraulic conductivity, concentration, rainfall are often taken before statistical analyses are performed. Transformations usually involve power functions of the form y, which is the log value equals sum x to the theta, where x is the untransformed data, y is the transformed data, and theta is the power of the exponent. So here's a nice ladders of power sort of framing, where we have 1, x, the original units where there's no transformation. And if we have negative skewness, we can see that we can square the data, we can cube the data all the way up to whatever power you need in order to correct the negative skewness. Or on the right-hand side, we can do the square roots, cube roots, the logs, reciprocal roots, and so forth in order to move the mean closer to the median. This is a good skill for you to have, to understand how to transform the data, do the analysis, and then remember to transform it back, because it is transformed data. It is y, no longer x, when you transform it. X is the value that you measure. It's the real value. Y is the transformed version. Make sure you understand how to go back. Now, graphical data is a critical form of data analysis and representation in hydrology. Graphs provide visual summaries of data which more quickly and completely describe essential information than do tables of numbers. Graphs are essential for two purposes. They provide insight for the analyst into the data under scrutiny, and they illustrate important concepts when presenting the results to others. Graphs are not analyses. Graphs are visualizations of data and analyses. The first of these tasks has been called the exploratory data analysis, EDA, because why not? EDA procedures often are or should be the first look at a data. So you get a bunch of data, the first thing to do is graph it. When I get a bunch of rainfall data, over time, even if it's 20 years worth of 15-minute data, I plot it. Because by plotting that, I can see where the storm events are, because they're clustered. I see plot the intensity of the event over time, and I can count real quickly the humps and the curves, and I can count how many storm events occurred over that period of record, even if it's 20 years. And I can also get a sense for what the extreme events were, the long ones and the intense ones. Patterns and theories of how the system behaves are developed by observing the data. We are ultimately observers of phenomena, and graphs allow us to observe phenomena, especially over time and with relationship to each other. These are inductive procedures. The data are summarized rather than tested. Their results provide guidance for the selection of appropriate deductive hypothetical testing procedures. A histogram is probably the most commonly used form for us in hydrology. Rainfall and flow histograms tell us a whole lot. Bars are drawn into height at the number, where height is the number n to the I, or fraction n to the I over n of data falling in one of several categories. So you categorize the data within ranges, or in Excel jargon, bins, and then we plot them. So in this case, the annual stream flow of the Licking River had this bin that looks like it's between 750 and 2250, with 1500 in the mean and the midpoint. It looks like 7 occurrences at that range. It had 22 occurrences at this high range. Now you can already see that there's a distribution starting to emerge here. And the more bins you have, the smaller these units are, the more continuous this starts to look. Well, that leads to the question, how many bins should you have? Could you just plot all the individual observations? Well, if you do, they're going to be noisy as all get out. That's the reason we summarize them in bins. So they have one primary deficiency. Their visual impression depends on the number of categories you select. Same data, up and down, top and bottom, exactly the same data. And look at the difference in the observations and how they look. Now you can still see a bit of a right skewness, a negative skewness of the data towards the right, of a central tendency. And you can still see that there's but still, this is quite different than this. The lower is quite different than the top. So these are bins. The number of bins you should have should be the log of n, the number of observations divided by 0.693, where you round that number, where the number, or k is round as the bin number rounded up. So if you get 6.8, then you use 7 bins. I repeat this. We have a way to calculate how many bins you have to have in order to get a pretty good statistical representation of your data. You have the number of bins is the natural log of the number of observations divided by 0.693. One of the other useful ways of plotting data are through cumulative frequency or quantile plots. Quantile plots visually portray the quantiles or percentiles, 1 to 100, of the distribution of sample data. So you can think of the cumulative frequency, 0% to 100% probabilities, as being probabilities on the y-axis. Quantiles of importance, such as the median, are easily discernible because you can go to the 50% quantile and boom, you find the median right here. So these are effectively empirical CDFs, cumulative distribution functions. So you fit this to a line and you have a CDF. Cumulative frequency plots have 3 advantages. Arbitrary categories are not required like in histograms. All of the data are displayed, unlike a box plot where you just have quartiles. Every point has a distinct position without overlap. So here's what you do if you want to create one of these. The data are ranked from smallest to largest. The smallest data, so you take a cumulative file of data. The smallest data are assigned a value of rank I equals 1. So your first data point, the smallest data point, in many cases, which is going to be 0.0001 for rainfall or flow, because we don't use zeros, is going to be listed 1, 2, 3, 4. The largest receives a rank I equals n, where n is the number of observations. So if you have a year's worth of daily data, you have n equals 365. If you have 10 years of 15-minute data, you have thousands of n. But you can still do this very nicely in Excel. That's why computers are useful. The data value themselves are plotted along one axis, usually the horizontal axis. On the other axis is the plotting position, which is a function of rank and sample size n. Now, you can use the Cunnane plotting position pi as well as a way to create these. Now, if I go back here, we're looking at the x-axis here is flow. And so each discrete flow value is just ranked from the lowest to the highest, and they're added. So this particular observation is 30% of all the data are less than this observation. 70% of this observation is higher than this observation. So that's one way to do this. But in this case, you can, if you plot on the x-axis the plotting position pi, you can create a probability distribution function. So if we look at QI, which is the data, individual data point, and then we can look at PI, the plotting position. Plotting position is the y-axis data point, and the observation is on the x-axis in this set. So that you have to be careful which way you put them. I've got them reversed in this description, but I see them both ways. PI equals the observation minus 0.4 divided by n times plus 2. It's a way to make these all proportional. So if you have 36,000 observations, you don't have 1 through 36,000. They're all represented as a proportion of the total. And this is a way to create proportionality in that distribution. So they're all represented as 0 to 1s. So you start out with 0.01 as a PI, you end up with 0.99 as the PI. And this is a way to convert these into a probability distribution function. They're an empirical version of the CDF data set. So the CDF is of a normal distribution plotted with cumulative frequency of this data set shown here. You can see that the cumulative distribution function, which is a numerical continuous data set, which is represented by an equation where you can calculate any data along the x-axis. If you know the y-axis, y equals some function of x, whereas the actual observed data follow, and you can see there's an alignment that's measurable, goodness of fit. Now, the three purposes of the cumulative frequency plots are to compare two or more data distributions, a QQ plot, for example, flow versus flow plot, to compare data to a normally distributed probability plot like we see here, or to calculate the frequencies of exceedance, a flow duration curve. So what you can see from this is if I ask you what's the 10% exceedance probability, well, it's 1 minus what you see here are 0.9. So that's the 10%. 1 minus 10 is 0.9, or 90%. So you can see that 90% of the data are less than this point, which means only 10% of the data are greater than this point. So this point would be somewhere in the 5,700 cubic feet per second range. So Licking River, I can say that 90% of the flows are less than 5,700 cubic feet per second for this period of record. You see how powerful that is? And look at the normal quantiles at the top. So the normal quantiles allow you to plot these as well as the Q's, the actual flows. So if you plot both, the normal quantiles on the x-axis on the top, stream flow on the bottom, now we start to see a normal distribution layout. And remember, these are standard deviations away from the mean, 1, 2s, and 3s. So if we know that 90% of the distribution of a normal distribution is 1.96 standard deviations away from the mean, we can come out here to a normal quantile of 1.96, draw a line down, and over here and draw a line down, and we can say 90% of the flow data are between these two lines, 1.96 quantiles, or Z alphas. Probability plots are used to determine how well data fit a theoretical distribution, such as a normal, log normal, or gamma distribution. Probability plots make visual data comparisons with theoretical distributions more discernible by expressing the theoretical distribution as a straight line, since departures from the distribution are more easily perceived. To construct a probability plot, quantiles of sample data on the y-axis are plotted against quantiles of the standardized theoretical distribution on the x-axis. A simple linear regression line with a coefficient of determination, r squared, is used for distribution of fit. Now, this is not a linear data set. You can't do this with this data set, but you can linearize this by linearizing the normal quantiles. That's what we're talking about. And you notice the way you do that is you compress them about the middle. So this is the same data presented with stream flow on the x-axis and normal quantiles on the y-axis. The median, the probability of 0.5 data, right here at 0, is clearly discernible for the stream flow. So the median stream flow for this data set is 4,079 cubic feet per second, which is the midpoint. The data are ranked from smallest to largest, corresponding with the positions pi, as we saw before. Normal quantiles, which are called z sub p's, for a given plotting position may be obtained by a table of standard normal distributions found in most statistics textbook, or you can look at our reference document, table B2 in the appendix, which presents standard normal quantiles for the Cunane plotting position table B1. So take a look at table B1 in the USGS statistics handbook referenced earlier in this lecture, and then found in your readings for this chapter. Alternatively, you can use probability paper, which is the way I learned to do it. The problem with this is you have to have probability paper, which is harder and harder to find. And the problem with that, of course, is also I have not yet found a good way to do this in Excel. There may be a good way. I have not yet found a good way other than using the system that this system with normal quantiles. Now again, the normal quantiles you see are, I misspoke earlier, they are equally distributed away from the mean, but the calculations capture the curved data. Because What you ultimately have is, in order to make this straight, is you have a compression of data around the middle to flatten this whole thing out. And that's the way you get a straight line. See? I'm sorry, compression of data on the edges. Spread it out in the middle. So the horizontal axis can be directly interpreted as the percentage probability of occurrence, the plotting a position of times 100. You have a chance of exceedance at the top or a chance of less than at the bottom, depending on how you enter the graph. So you have 99% of the data, or 90% of the data are larger than this point, or 10% or less than this point. Pretty straightforward. If probability plots do not exhibit a linear pattern, their nonlinearity will indicate why the data do not fit the theoretical distribution. This is additional information that hypothesis tests for normality do not provide. So the three conditions resulting in deviations from linearity. If you have nonlinear data, that means you have skewness or asymmetry of your data, you have big outliers, and you have heavy tails of the distributions. Probability plots can be used to indicate what type of transformation is needed to make your data more symmetrical. The degree of curvature gives some indication of the severity of the skewness, and therefore the degree of transformation required. Remember our ladder of transformation that we talked about earlier in this lecture. Direct comparisons can be made between two data sets by graphing the quantiles of one versus the quantiles of the other. That's a quantile-quantile plot. If the two data sets came from the same distribution, the quantile pairs would plot along a straight line, where yp equals xp. So y-axis and x-axis, it's a linear relationship. P is the plotting position of y and the pth quantile of y. In this case, it would be said that the median, the quartiles and the 10th and 90th percentiles of the two data sets are equal. If one data set had the same shape as the second, differing only by an additive amount, each quantile was 5 units higher or lower, the quantile pairs would fall along a line parallel but offset by some amount, but with the same slope, or with a slope of 1. Several aspects of the relationship between the data sets are immediately seen then. If we look at these data, yields with fractures, yields without fractures, with two different types of data. The lowest 9 quantile pairs appear to fall along a straight line. See these 9? Look at this, straight line. With a slope greater than 1, not parallel to this slope. This indicates a multiplicative relationship between the data, where y is approximately 4.4 times x, where 4.4 is the slope of the data on the plot. The yields with fractures, that is, if we think about this as these are data yields from water. Yields mean amount of water you can get in gallons per minute per foot. Where you have fractures versus where you don't have fractures, yield with fractures in the substrata yield 4.4 times the amount of water for the lowest 75% of the data, but then converge at the high end. The three highest yields return to the near linear relationship. So low yields produce faster with fractures, but at high yields it doesn't matter. They converge. So you can see these relationships. This is the way you interpret a QQ plot. This leads to a discussion about uncertainty. Uncertainty is just what is not known. There are unknowns, there are known knowns and unknown knowns. They are typically referred to as no-uncs, that is known unknowns, and unk-uncs, unknowns unknowns. The sample median and sample mean estimate the corresponding center of a population. The estimates are called point estimates. By themselves, they don't portray the reliability or lack of reliability, variability of the estimates. Interval estimates are intervals which have a stated probability of containing the true population value. We can be 90% confident that the value resides between this number and that number. The intervals are wider for a data set having greater variability. Interval estimates can provide two pieces of information which point estimates cannot: a statement of the probability or likelihood that the intervals contain a true population value, that is its reliability, we call those confidence intervals, or a statement of the likelihood that a single data point with this specified magnitude comes from a population under the study. that is a predictive interval. Confidence interval, what's the likelihood that the interval contains the true population? Predictive interval, what's the likelihood that the data point with a specific magnitude comes from that population? Confidence intervals are the probability that the interval does include the true value. The probability that the interval will not cover the true value as the alpha level is computed as 1 minus the confidence level. So if you want to be 90% confident that data are within, or to analyze a data point's 90% confidence interval, you would use an alpha of 0.1 or 1 minus 0.9. The width of the confidence interval is a function of the shape of the data distribution, its variability and skewness, the sample size, and the confidence desired, the alpha. As the confidence level increases, the interval width also increases, because a larger interval is more likely to contain the true value than a shorter interval. That is, a 50% confidence or an alpha of 0.5 is going to have a narrow range of confidence. An alpha of 0.05, which is 95% confidence, is going to have a wide range. Symmetrical confidence intervals to the mean are computed using a table of students' t distributions. You can find that in Excel with confidence.t with an alpha, a standard deviation, and a number. That'll give you the t value. The width of the confidence interval is a function of these critical values, the standard deviation of the data, and the sample size. For a point estimator, the upper and lower confidence intervals can be calculated from the mean minus the t alpha divided by 2 to n minus 1 times the square root of the standard deviation over n, and the mean plus that variable. So typically that would be like the t alpha of 2 times n minus 1 is usually something in the range of 2.14, and then times the square root of the variance, which is the standard deviation. The sample mean arsenic concentration for a sample C equals 98.4. This is the point estimator for a true unknown population with a mean of mu. With an alpha of 0.05, confidence interval on mu is 98.4 minus the t value times the square root of its variance, which we know the variance is 144.7. So the square root of that squared over 25 observations. So if this is, notice it's n here, and the upper one is n minus 1. So s squared, so it's 12 point something would be the standard deviation. 98.4 is the mean. So you can calculate this, and you can see that we can be 95% confident that the concentration of arsenic in our sample is between 38.7 and 158.1. I said lead here, it's actually arsenic. Assuming the symmetrical confidence interval is appropriate. This is why symmetry matters about the mean and median. This is why skewness is a problem. Is when we have skewed data, it can skew our confidence intervals up and down. If the largest value of 580 were changed to 380, the median and its confidence intervals would be unaffected by this, but C would change to 90.4 with a 95% confidence interval changing dramatically. So what if you have skewed data? Means and confidence intervals may be computed by assuming that log values, log of x, natural log of x data are symmetrical. So you do a log transformation. If the data appear if they're positive skewed, if the data appear more like a log normal than a normal distribution, this assumption will give a more reliable, lower variance estimate of the mean than will computation of the sample without log transformation. So to estimate this population mean mu of x in original units, assumed data are log normal. 1/2 the variance of the logarithm is added to y, meaning of the mean of the logs prior to the exponentiation. This is an important, we'll talk about this in the next couple of slides, but this is an important thing, that you actually have to shift the mean a little bit in order to adjust this. As the sample variance is s squared y is only an estimate of the true variance of the logarithms, sample s to the mean is biased. However, for small variances and large sample size, this bias is not particularly a concern, and most of our data meet that criteria. So mu hat x equals the exponential of y, average of y plus 0.5 times the variance of y, or y equals the natural log of x. So y bar, the mean of y equals the sample mean, and s squared y equals the sample variance in natural log units. So we have alpha over 2 here, alpha over 2 here. Now what does that mean? That means if you want to be 90% confident, then this is 5% of the data over here, and this is 5% of the data over here, alpha over 2, because we have 90% of the data here, 1 minus alpha. That's the 90% confidence interval. If you want to be 95% confident, then each of these are 2.5% of all the observations. 2.5% here, 2.5% here. That's why we divide alpha by 2 when we want to know what the two-tailed T confidence interval is. We're simply asking what are the data between the lines under this curve with lower and upper confidence intervals. And all we can say about with this approach, all we can say is that we're confident that the mean x lies between these two lower and upper limits based upon that confidence level. So again, calculating this is fairly straightforward. So we calculate mu x, estimator mu x minus t alpha times the variance of y, square root over n, square root of that. That's the lower, and the upper one is this variance times t alpha times the variance added to it. Remembering that mu x is calculated differently for each circumstance. We add 0.5 times the variance to the mean, y mean, in order to calculate it. Calculating uncertainty for asymmetric skewed data gives you the ability to actually see your variance when you plot the log of Q versus some data set. So total dissolved solids, we see the mean, the solid line, we see all the data points, and we can see the 95% confidence interval about the mean. That's the 95% of the regression line, not of the data. So the confidence intervals about the regression line are captured within these dashed lines. We can be 95% confident the regression line will move between these dashed lines. 90% confidence. So this is a cloud. Think of this between these dashed lines as the cloud of regression line. If we want to be 90% confident of the data themselves, then the dashed lines show that. And you notice that most of the data are contained within the dashed lines. This is for a parametric analysis. And if we modify for skewness, we can see that we actually shift up a little bit. We shift these dashed lines. The dotted line here, we've abandoned our standard deviation distribution. This is simply a comparison between non-skewed and skewed. This is when we add half the standard deviation to the means. We move it up a little bit. That's what skewness does. So we move this lower limits up and the upper limits up. It's a lot of information for you. Make sure you take a look at the documents, and again, always provide a reminder that this is where that we have lots of rainfall and flow data available that we'll be digging into in homeworks this week and future lectures. So please dig in, go to these sites, get familiar with them. These are resource sites. Download that USGS document, have it available. I've only covered a very brief set of materials. If there are things I didn't cover effectively or to your satisfaction, that document covers them much more extensively with citations. Dig a little deeper. You can find all sorts of YouTube descriptions of what we just described in Khan Academy and other resources, Engineering Toolbox and others. And certainly don't hesitate to ask me if you have questions about our process. Thank you for your attention during this relatively long lecture.